Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving an interesting problem with complex numbers. This problem looks familiar. Hopefully I haven't made this video before. If I did, apologize, but hopefully you're going to learn something new from this video. And if you can find the other problem, let us know in the comment section. I know you guys are better at finding my videos because I have too many videos. By the way, I have another channel called Cyber Math that focuses on number theory, trigonometry, and algebra, but mainly algebra, heavily algebra, if you like algebra, and a little bit of geometry here and there. I'm still thinking of a good geometry problem that I can solve. Maybe you have some suggestions. Feel free to let us know. And always comment down below what you think, and let's try to be positive as much as we can, okay? Great, so what are we going to do? Z is a complex number. And what are complex numbers? Complex numbers can be written as a plus bi as well as r times e to the I theta, and I'll talk about these in little detail. If you want more details, go ahead and check out my lecture videos. I made a bunch of videos on basics of complex numbers. Great. Now, basically, here's our criteria. Z is a complex number. K is a real number. So let me make sure ahead of time that you know this, because I know some people are going to say, what happens if it's not a real number, right? We can also look at that as a bonus towards the end. But let's go ahead and first assume K is real, okay? So that this works. On the left-hand side, we have the sum of two complex numbers. How can K be real? That's a good question, right? So let's go ahead and see. And I'd like to provide two methods. Let's start with the first one. Great. So Z is a complex number, and I could definitely, and you could probably talk about three different methods. Maybe if I can come up with extras, I'll later on let you know. But for now, I just want to go ahead and multiply both sides by Z. Z squared plus 1 equals KZ, okay? Now, what does that mean? This means it's a quadratic equation. It's quadratic in Z, so we can solve it, hopefully, right, with the help of the quadratic formula. We don't know what K is, but you can think of K as a parameter. This is an equation with a parameter, which means there's actually a family of solutions, not a single one, but depending on the value of K, you can get infinitely many solutions. Each time, you're going to have a different solution. But are there always solutions? That's another good question to ask. That's why I like these kinds of problems, because it's kind of open-ended, sort of. And this is something that's hard to guess. Can you guess what Z is going to be like? Hard to guess, right? That's why I like these kinds of problems. You kind of have to show your work and, prove. So, what was I saying? I kind of lost my train of thought. Maybe the train will come again, hopefully. But the main idea is trying to use this quadratic formula, right? Let's proceed with that. I'll hopefully remember. Quadratic formula tells us negative b plus minus the square root of b squared, which is k squared, minus 4ac, which is minus 4, divided by 2. That's it? You got the solutions? Well, here's what I was trying to say. Do we have solutions for all values of k? That's a good question, right? Don't you think? For example, what happens if k is 0? Let's go ahead and explore. So if k is 0, then z is going to be 0 plus minus the square root of negative 4 divided by 2. So the square root of negative 4 is 2i. There are two square roots, but the plus minus sign will take care of it. So we can write it as 2i divided by 2, and that'll give us, of course, there's a plus minus. I forgot to write that. The answer is plus minus I. So z equals I is a solution. What does that mean? Well, if z plus 1 over z is equal to 0, that means I and negative I are solutions. Of course, there are two solutions, right? But have you noticed something about the solutions? Let me not say that right now, okay? Let's not spoil the surprise. But basically, for different different values of k, you can find solutions. That's what I meant by a family of solutions. For example, if k is equal to square root of 3, why am I picking these weird values? Because I still want this to be non-real. That'll be 3 minus 4, which is negative 1. The square root of negative 1 would be I. So it'll look like this. Z would look like square root of 3 plus minus I divided by 2. And that should definitely be familiar to you. And now that'll be like root 3 over 2 plus minus 1/2 I. Does that number look familiar? If not, check it out. I mean, check out the lecture videos. Hopefully someone can post the answer. But those are special numbers. Anyways, you get the idea. We have a bunch of solutions, and depending on the k value, we get this particular solution. Well, so what does that mean? Does that mean z is never real? Can z be real? That's a good question, right? Now let's go back here. Z plus 1 over z equals k. Now we said that k is real. And if z is real, can the sum of z and 1 over z equal k? Absolutely. Think about it. If k squared is greater than 4 or equal to, which means if k is greater than or equal to 2 or k is less than or equal to negative 2, let's take k equals 3, then you will get a real solution. Why? 3 plus minus, that'll be 3 squared, 9 minus 4, 5. Uh-oh, we're going to get something that is associated with the golden ratio, don't you think? Yeah. So, but all these solutions, if you look at all these solutions, what do you see in common? Do you see something in common? Let us know in the comment section down below if you do. Because I'm about to start the second solution, which hopefully will shed more light on that thing that you're supposed to be seeing. Z plus 1 over z is equal to k. Now, there are two things that you should notice if you haven't. First of all, we're adding z and 1 over z, and at the end we're getting a real number. When does that happen? That only happens if you add two complex conjugates. What is that supposed to mean? For example, take 3 plus 4i. What number should I add to this so that the answer is a real number? Well, 1 over 3 plus 4i is, let's take a look. This will be 3 plus 4i plus, well, here's the answer. First of all, let me answer my question. 3 minus 4i needs to be added. You could also add 7 minus 4i, but with the reciprocal, things are a little different. Okay, let's just say we add 3 minus 4i. Okay, so this should work. But when you flip this number, you have to multiply by the conjugates. And that'll give you a 5, which messes up everything. The 4i is not going to cancel out. Uh-oh, that means you are not supposed to have a number in the denominator. In other words, z and 1 over z need to be complex conjugates. But not only that, the modulus also needs to be 1. Does that make sense? Okay, here's what you can do to get a better understanding. Let's write z as r times cosine theta plus I sine theta. Now, first of all, notice that if I add z and 1 over z, if I add z plus 1 over z, there's going to be an issue with the r, don't you think? Yes. So r needs to be 1, first of all. You don't want r to come up because you're going to get something like r squared, which has to be 1. So forget about r, and let's just add these things. And when you add those two things, you find the following. This multiplied by the conjugate thing, cosine theta minus sine theta, divided by cosine squared plus sine squared, which is equal to 1, by the way. So you're going to end up with something like this, and everything will work out because everything is awesome. And you're going to end up with 2 cosine theta. That is interesting. So z can be written as e to the I theta, and from here, 1 over z would be e to the power negative I theta, I'd like to say, yep, I think so. Of course, r is 1 in this case. And z plus 1 over z would be 2 cosine theta, which is k. So from here, cosine theta would be k over 2. And sine theta, who knows what, right? And then you can kind of put it in this form. Find theta from here, and that should give you the same solutions we were just looking at, right? Hopefully. Okay, but how do we find the fact that from here, z and 1 over z have to be complex conjugates? So hopefully from here, using these facts, you can arrive at the same solution. And let me know what you think, because this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care. Don't forget to check out Cyber Math and aplusbi, and bye-bye.